Our third section in this CO1 is the fabrication of NMOS, PMOS and CMOS technologies. So, let us discuss about the NMOS fabrication process flow. So, usually the general aspects of the polysilicon gate aligned in a NMOS fabrication and which will start from the fabrication. So, here the appreciation of the fabrication flow will give always an insight into the way in which the design information must be presented, and also into the reasons of certain performance characteristics and limitations are also be presented. So, let us see here the number of the steps which are involving the complete fabrication process flow of the NMOS. The first step is the processing is carried out on a thin wafer cut from a silicon crystal of the silicon of high purity into which required P impurities are introduced. So, this is the wafer we have taken and we have introduced into the a number of the impurities into it. This is basically a P type of the substrate, and here these wafers are in different diameter, 75 mm diameter to 150 mm diameters, and also the different thicknesses. It is 0.4 mm thickness of the thickness, and here the impurity concentrations of this wafer is considered 10 to the power of 15 per centimeter cube to 10 to the power of 16, which is normally having an approximately the resistivity range is 25 ohms to 2 ohm centimeters. So, such a kind of the wafer we require, because always the wafers are the building block of any kind of the device. The second one is a layer of the silicon oxide. So, silicon oxide layer is deposited. Usually a thick grown all over the surface of wafer to be protect the surface. So, act as a barrier to doping during the process and provides a general insulating substrate on which the other layers are also can be able to deposit and pattern. Then the third step is the we need to be do the surface is now covered with the photoresistive which is deposited onto a wafer. So, you can see the third step is the photoresistive layer, and this is a spun to achieve an even distribution of a required thickness. This is the photoresistive layer. In the fourth step, the photoresistive layer can be exposed with the ultraviolet light source that will be passing through the mask, and therefore diffusions into take place together, the transistor channels can be formed. And assume that, for example, these areas are exposed to ultraviolet radiations or the polymerized, which is very hardened, but the areas are required to diffuse or the shielded by the mask and then unaffected. So, wherever it is passing through the mask will be provided, then the pattern will be formed like this. Therefore, in the fifth step, what we can do, the areas are subsequently readily etched away together under the silicon oxide. Therefore, the wafer surface is exposed with window defined mask, and then in the sixth step we go with the polysilicon deposited on the top of these to the gate structure formation. And in these steps, what we generally use in the deposition process is the chemical vapor deposition. By this chemical vapor deposition process, we do the fabrication of a very fine the pattern devices, and which is precisely control the thickness, impurity concentrations, and resistivity is increases. And the seventh step, what we can do is the photoresistive coating and mask, which will allow the polysilicon to be patterned, and in this way we can to form the diffuser to form the source and the drains, which is showing here. So, the diffusion is achieved by heating wafer to a very high temperature and possessing the passing a gas contain the desired n type of the impurities will be happened, and which will be the phosphorus kind of the materials. And the thick oxide, that is the silicon oxide, is grown all over the surface. The drain and the source areas are connected, which is based on the contact cuts to be made, and the whole chip has to be metallizations with the aluminum materials, and its surface thickness typically 1 micrometer. Then therefore interconnections patterns can be formed. The layers are diffused with the substrate, and the polysilicon oxide on the substrate, metal insulating again by oxide to form the depletion mode devices. Only necessary introduce a masked ion implantation process from steps 5 to 6 or 6 and 7. So, we have to do this process again and again the thick oxide act as a mask, and this process take the self alignment. Considering of all these processing steps, number of steps, some steps will be repeat again and again, we will have a relatively few masks are needed. The self alignment aspects of the masking process greatly is the problem of the mask registration. So in practice, some extra process steps are required, because whatever we have seen, the 9 steps, some of the steps will be repeat, and overall we required number of the more steps, and to get the chip into the actual reality. So in this way, the summary of the NMOS process is, it is given here in number of the steps: processing, mask patterning 1, mask patterning 2, mask 3 deposition, and disk diffusion by n plus diffusion, and mask 4, mask 5 deposition, mask 6, and all. And by this is the essence of the NMOS transistor fabrication process flow. This NMOS fabrication process flow or the PMOS fabrication process flow, the difference is only the substrate and other layers. Once we understand the NMOS fabrication process flow, the PMOS fabrication process flow can be understood. The NMOS and PMOS fabrication steps and also the fabrication will be involved, and it will be performed only in a very highly sophisticated laboratory that is called clean room technology. These kind of the IC fabrication techniques cannot be done in a normal laboratories. It requires very highly sophisticated laboratories where it will be free from the contaminations, and it will be free from many kind of the other kind of the contaminations. Therefore, the efficiency of the device, the performance of the device is greatly improved. So we can understand the NMOS fabrication process flow similar to the PMOS, and then we have a CMOS fabrication. So in the CMOS fabrications, we have a number of the approaches: P-well, N-well, and twin tub and silicon on insulators. So here all these 4 techniques can be utilized to do the fabrications of these. P-well process widely used in practice. N-well process is also very popular in this process, and twin tub and the other silicon on insulator process are also be greatly used. So the fabrications of the P-well process, already we have seen the PMOS and NMOS. It is the P-well process. The fabrication steps are maintained with reference to the previous fabrication flow is almost all similar to form the NMOS. So it is nothing, basic process steps are same nature as of those which is used in the NMOS, and here you can see the other steps which are formed to the P-well process. So what we used to have the P-well process is we will create some kind of a well here with the P type of the material, which is the what is 4 to 5 micrometer thickness of the P-well steps. So that well will be formed at one side, and we used to be say this is a P-well process. You can see here this is a one transistor which is a NMOS transistor, where here P-well is formed, and in the P-well, that is the P type of the substrate, therefore NMOS is created here. So both NMOS and PMOS which is formed and by the P-well process, therefore here we have both combination of NMOS and PMOS technologies, and NMOS and PMOS complementary will be worked together. The summary of these critical steps involved in the P-well process is mask 1, mask 2, mask 3, mask 4, mask 5, mask 6, mask 7 and mask 8. The overall mask 8 is the overall passivation layer is applied, and mask 8 is needed to be defined the access to be bonding pads. So this is the other type of the technique, which is the N-well process, and this is a reverse to the P-well process, and the steps are involved here: formation of the N-well regions, and we will define the NMOS and PMOS active regions. We have a field and gate oxide, we have a form and pattern polysilicon, we have a P plus diffusion, N plus diffusion, contact cuts, deposit, pattern metallizations, overall glass with cuts and bonding pads. So the formation N-well regions, define NMOS and PMOS, field and gate. These all the steps will be processed in the N-well process to get the CMOS transistor. So we have a transistor which is a here we have a N well, and here we have a PMOS, and from this we have a PMOS, and overall we have NMOS here. Therefore, the total together will be act as a CMOS. So, always the CMOS technology will be provided a very high speed and also high density of the elements in a circuits. There will be always some problems in this process, which is the latch up problems. Latch up problems are considerably reduced when we go with the low resistivity epitaxial P type of the substrate. So, the starting material we will be we use very low resistive materials. Therefore, the N well process is the performance already purely performed P transistors. So, the design rules always presents 1.2 micrometer and 2 micrometer technologies of the design rules will always provide you type of the informations about the avoiding of the latch up problems. So, like this, the NMOS technology by NMOS fabrication, PMOS technology, PMOS fabrications by these two combinations P well and N well will be used to form the CMOS transistor. CMOS transistor is a combination of NMOS and PMOS transistor, and which will be work together complementary. In this process, in this regards, we have discussed the fabrication process, a number of the steps, how we can fabricate the transistor of the NMOS, PMOS and CMOS transistors. Thank you.